Okay, so the topics of absorption and filtration are really high yield on board exams and also on med school exams. And so this is a really high yield page. But just to start off, this does come up every once in a while, these three types of capillaries: continuous, fenestrated, and sinusoid. So with continuous, right here, you can think of the blood-brain barrier where stuff doesn't get through very easily. Fenestrated, stuff does get through. I always think of the kidney, and then for the sinusoid, I think of the liver. Anyway, not highly tested, but these next two things you can put a star by: the Starling equation and then this absorption filtration thing here. These are tested a lot, and the good news is that if you approach it right, you can get these questions right every time. So, looking at the Starling equation, you don't really have to worry too much about the reflection coefficient, except on cell physiology tests. This KF thing, you don't really need to worry about. That's more of a properties of the membrane that you're trying to pass through. But these other four things are really important. And so what it is we have a pressure inside the capillary. So we have a hydrostatic pressure. I'll draw it over here. There's a hydrostatic pressure inside the capillary, and that's the pressure pushing stuff out. So it would be transmural pressure. So going across a wall, you're going across something, and mural stands for wall, as opposed to, and I'll just say the perfusion pressure, you can think of that as the pressure that's pushing stuff forward. So I just drew another arrow, and so it'd be the difference between the pressure over here, if this is the beginning, if this is the arterial side, it'd be the difference between the pressure here and the pressure in the venous side. So that would be the perfusion pressure, whereas the transmural would be going out. So anyway, okay, so there's like I said, there is hydrostatic pressure inside the capillary, and there's also hydrostatic pressure outside the capillary. You wouldn't think of there being hydrostatic pressure outside the capillary, but there just is. It's usually a low number. And then you also have another type of pressure, which is a little counterintuitive. You have the osmotic pressure, and the osmotic pressure, it pulls stuff in. So hydrostatic pushes stuff out, whereas osmotic pressure pulls stuff in. And then in the tissue, you have osmotic pressure also, and does the exact opposite. So here's how you approach a question. Let's say it gives you 3 of the values, or they can either give you 4 of the values and want you to tell. They ask the net pressure, or they might give you the net pressure and 3 of the values and ask you to solve for the one missing one. But all you do is you just draw some arrows, and you say, so if they say the capillary hydrostatic pressure is 10, you just do an arrow like that and do 10. And then if they say the capillary osmotic pressure is, let's say 2, you draw an arrow this way and do a 2. And then if they say the tissue pressure is, let's just say 2, then you draw an arrow like that and put a 2 by it. And then if they say the capillary or the tissue osmotic pressure is 5, you draw an arrow like that and you put a 5 there. And then all you have to do is add up your arrows and come up with the pressure, and it's very easy. So these questions here, easy to get right every single time. Okay, this next one is also very high yield, and so what's going on here is you have, as you know, as the blood enters the arterial side of a capillary, you got a high hydrostatic pressure, and the fluid is being pushed out. It's being filtered, and then it comes back around and it enters back in on the venous side. And the reason why is because as more fluid exits and we get further down, you can see that there's a much bigger concentration of these little blue things here than there are of these little red things over here, so which are osmoles. So there's more osmotic pressure pulling the stuff in at the end of the capillary. So about 90% of what is filtered comes back in, and then the 10% that does not come back in goes back in through the lymphatic system. So this is how you should approach questions like this. And I'm going to open a new screen. So let's see here. Okay, so what you should do is you should just draw a box. And let me draw a box here. Let's see. Need a pen. Okay, so if you draw a box, and then if you make a line like this, and then if you make a dotted line like this, and a dotted line like this, okay, this is how you approach it. Okay, so I'm just going to throw out some numbers. Let's say they say let's put a 40 here. That's the hydrostatic pressure coming in. So remember this. So this would be the hydrostatic pressure going down as you go down the length of the capillary. And let's just say at the end of the capillary, it's like 15 or something like that. Okay. So and then in the middle of the capillary, that's when the fluid goes from being filtered here to being absorbed here, right at this line right here in the middle. And so the way a lot of questions work is they'll say something's changed, and then they want you to say whether you're going to have more absorption, whether you're going to have more filtration, or whatever. So let's say they say that that the arterial constricts. So remember, the arterial feeds into the capillary, and it has that it is where that smooth muscle can constrict and can regulate blood flow. So let's say that the arterial constricts. Well, what's going to happen? What's going to be different in this diagram? What's going to be different is that this line is going to shift to here like this. And so you can see now that it's going to be right here where fluid's going to start coming back into the capillary, in this entire distance right here. So it's going to have a net absorption. Whereas if, let's say, the question says that the arterial vasodilates, then the thing that changed is the line now is moving this way. And so you can see here, now the hydrostatic pressure is going to be much higher, and you're going to have to wait all the way till you get to here for stuff to be reabsorbed. So you're going to have a net outflow of fluid, because the fluid's going to be coming out from there to there. So, and that's really sloppy right there. I'm going to circle it. Okay. So basically that's the way you should approach these questions, is whatever the question says, draw the normal and then say what changed on this diagram, and then determine whether what's going to be different. So generally like with the example of the arterial vasodilation, you would have more fluid being filtered out than coming back in. And so a very important thing to know about is edema, which just means more fluid in the tissues and swelling and stuff like that. So I hope that helps.